Is going to tell us how sailboats work.
That's correct. And I was hoping that people would think that sailboat is a metaphor for something, but it's not. I'm literally going to talk about sailboats. I will try to give some sense of why an astrophysicist would care about sailboats, but it might not work very well. What do I want to say? So first of all, I should say that this is stuff I've been doing with Matt Claiborne. So the paper doesn't exist. Well, the paper does kind of exist actually, but we've been working on this for a long time, and it's like both of our 15th priority, so it's not done. But I will tell you a little bit about where we're at, and I think we have some results. I'm kind of excited. Of course, sailboats are understood phenomena. There's nothing not understood about sailboats. Well, there's some details. So the question is, why would we study sailboats? So there's several motivations. I want to say a few things, motivations, a few results we have, and then I will talk about the details. Okay, so the first motivation, which originally got Matt and me talking about this problem, was the problem that's known as DDW, FTTW. This problem, have people heard of this? This problem is directly downwind faster than the wind. That's a physics problem in classical physics. And the question is, can you make a device that using only wind power travels downwind faster than the wind?
Yes.
Nice question. The answer is yes. In fact, the answer is obviously yes. This is how we got started, because Matt and I agreed that it was obviously yes. But there's a bunch of theoretical physicists who believe the answer is obviously no. There is a ton of stuff on YouTube about this, which is extremely amusing. If you've got a few hours of YouTube and you want to nerd out, look up directly downwind faster than the wind. There's tons of funny things. And people have built all sorts of hilarious devices that do seem to travel downwind faster than the wind.
By the way, do you or Matt sail?
No. Actually, the first line of our paper is that we're not sailors, which maybe undermines our authority. In fact, I did used to sail when I was in high school. I was a competitive sailor, but I have not sailed since high school or college, maybe. Sail? A little bit. Oh, Matt's actually been on an ice boat, I believe, which is even better.
Near an ice boat.
Near an ice boat. Ice boats are in a certain regime, which is kind of interesting. I'm not going to talk about ice boats really. I'm also not going to talk about solar sails, which is also a very interesting thing for space technology, and there's a lot of work going on that. But anyway, we were inspired partly by this directly downwind faster than the wind, because a sailboat is a model system to think about that problem. It's a very simple system. The devices that people build in this debate are quite complex devices that involve wheels and gears and propellers, and a sailboat's a much simpler device, so it's kind of interesting. And we believe that we believe that you can go directly downwind faster than the wind. We believe that's demonstrated in a lot of ways, but in particular, we have a demonstration within the context of sailboats. Although some people wouldn't accept our answer to that problem, but I'll show it to you before this talk is over. Another thing that I was inspired by is I'm interested in the properties of ram pressure or drag, like air resistance. I've been interested in this for a long time, partly because it comes up a lot in astrophysics. It's an important property in astrophysics. Whenever you have two fluids that pass into each other, there's momentum transport between those two fluids, and that's called ram pressure. And there's like galaxies that have their ram pressure stripped out of them. When a galaxy with gas in it falls into a galaxy cluster, just the pressure of the intercluster medium can blow the gas out of the galaxy and shut off star formation, things like that. So ram pressure is what you traditionally call drag. And for instance, I'm interested in this also because I teach intro physics. By the way, the theme of all my brown bags for the last little while is that I only do things that are in the scope of intro physics. And in intro physics, ram pressure is the drag force. So if you throw a penny off a building, famously you can calculate that it should drill into the sidewalk, but it doesn't. It just goes clink on the ground. Why? Because it hits terminal velocity in just 1.5 meters or something. That's easy to understand in terms of ram pressure. Or golfers can shoot a golf ball or some golf on the TV. They can hit a golf ball 280 yards or something. Nothing can make a golf ball go 3,000 yards, no matter what. You could hire the US Army and they couldn't make a golf ball go 3,000 yards. The 280 yards is set by ram pressure. You just lose, you would, to go further than that, you'd have to hit the ball so hard it would ablate in the atmosphere. It wouldn't actually go. So ram pressure is like really important to day-to-day life as well as astrophysics. But day-to-day life is astrophysics, by the way, because we are macroscopic objects and we're always in like the convective limit. We're never in the viscous limit. You've never experienced viscosity, you won't. We live in the macroscopic limit, high Reynolds number world. Okay, and then the last thing I'm interested, the last motivation for me is symmetries. I've been interested in boring symmetries like rotation symmetry, Lorentz symmetry, translation symmetries. I've been interested in just really basic symmetries because first of all, I teach them in intro physics, and second of all, I have this feeling that we can improve data analysis and machine learning and things like that by introducing these symmetries. And so one of the things that was kind of a fun idea here was, can we write down a model of a sailboat that is a pure momentum transport ram pressure model and was exactly relativistically symmetric. So like a symmetric relativistic model of a spacecraft, of a sailboat. And you might think, well, special relativity can't matter because we're not working near the speed of light. That's true, it's just Galilean relativity. But if you want, we can show how it would derive from special relativity if you want. I'm not gonna do that right now, but I know how to do that. Okay, good. Good. So I mentioned astrophysics. So this is the only real connection to astrophysics. This is kind of a connection for me to machine learning and data analysis. And this is a physics problem of theoretical interest. By the way, this talk will be 100% theoretical. There will be no data, which is weird because I don't actually do theory. This will be my first ever theoretical physics paper.
Will there be a Lagrangian in your talk?
Say again?
Will there be a Lagrangian in your talk?
No, there will not be a Lagrangian. In fact, we're going to write this down. I'm going to write down equations for forces, which my Lagrangian friends tell me are illegitimate, and you should always write it in terms of Lagrangian or Hamiltonian. There are no forces. Fine. Okay, good. Now, I want to say that I wanted to say a little bit about our conclusions because I don't like to get into the rush at the end. So let me just tell you a few things we figured out by looking at sailboats. So one thing we figured out is that the answer to question 1 is yes. You can go directly downwind faster than the wind. But with a slight, I have to like complexify that a little bit, but that is our answer. One thing we figured out is that when we were doing all this, sailboats, we're going to do a very trivial model of a sailboat, unbelievably trivial. We're going to throw away all of the details of the sailboat. And sailboats have these beautifully engineered sails. In fact, if you look at America's Cup boats, the sails are actually woven on a non-flat surface so that they have intrinsic two-dimensional curvature and stuff. The sails are outrageously complicated objects. We're going to treat the sail like a block of plywood. So the model's terrible that we're going to use. However, when we think about the details of the sail being curved in the wind, we realize that it should also benefit these boats to have their keels curved in the wind of the water. The keels should also be curved. And so we were like, why are sails curved and keels aren't? And then it turns out for America's Cup boats, keels are curved. And they set the curvature of the trailing edge of the keel as they sail. So we predicted curved keels. Another thing we figured out is if you look at an America's Cup boat looks like this. It has a huge sail, and it has a very small body, and it has a tiny little centerboard. That's what an America's Cup boat looks like. If you go buy a yacht, don't do that. But if you do go buy a yacht that you commercially would just buy, like if you're a well-off oligarch, looks like this. It has a huge keel. We figured out why commercial boats have huge keels and professional boats have tiny keels. Hopefully I will answer that before we end. There's various other things we figured out. I'll talk about some of them as we go. Okay, good. Good. Questions? before I start. It's gonna get detail-y fast now. Yeah.
Right, so the boat manufacturers know this, right?
They know. Actually, one thing that's very interesting is, so there's many books. There's like 7 entire books written on the physics of sailing. I have now read all 7 of those books. That was very painful. We have an annotated bibliography for those books. Some of them are terrible. Some of them are technically totally wrong. But the ones that aren't wrong are very good, lots of good physics, and they reject the model that I'm about to put as way too simplistic. They're not even going to consider such things, and then then the books are all about the shape of the hull, the curvature of the sail, the length of the hull relative to the wind speed, and all sorts of things like that, which we're not even going to think about. So all of these things are basically known, and this design is very deliberate, and these things are modeled with like finite element systems with no really clean theory. The theory is finite element engineering systems. That's how they do this. And they figured out that you don't have to be smart to sail this boat upwind. You do have to be smart to sail this boat upwind. And they figured that out. So if you want to build a boat with high tolerances where any idiot can be drunk and sail upwind, this is the boat you do. Anyway, I'll show you that result in a moment. Okay, good. Okay, so if we're gonna make, so one thing, I got people mad on Twitter. I tweeted about some properties of this thing, and people got mad on Twitter because people on Twitter tend to be nerds. And sailing nerds get really upset if you ignore the details. And we're gonna ignore all the details. So the sailing nerds were upset by things like, we're gonna ignore all details of the shape of the sail, the boat, everything else. We're going to treat the boat as, we're going to make the spherical cow approximation to the sailboat in a moment. A truly spherical cow doesn't actually sail non-trivially, so we do have to add a sail and a keel to it. So we're going to kill all of that stuff. We're going to forget about it. Another thing we're going to forget about is that the wind is gusty, and actually a lot of sailing is about working off the variance of the wind rather than the steady wind. It's about the variance in the wind. We're going to ignore all that. We're only going to think about the steady wind case, because the gusty wind case involves a bunch of higher order things, which, you know, is too boring for us. And then another thing we're going to ignore is that there's what you might call velocity shear, meaning the velocity of the surface water in general in a river is different than the velocity down deep, and the velocity of the air at high altitude is generally different from the air at the surface. We're going to ignore that too, although I think that's easier to manage. And we're going to, oh, by the way, one of the reasons we're going to ignore all of this is we're going to work in the limit that the Reynolds number goes to infinity. So we're going to be thinking in terms, and boats have huge Reynolds numbers, like 10 to the 6-ish are the Reynolds numbers, meaning that viscosity is irrelevant. Now, it's not actually relevant. Viscosity, it turns out, is not actually irrelevant. It actually sets some details of the drag coefficients that are going to appear here. So the viscosity actually does matter, but we're only going to treat the viscosity in the sense that there's effectively some drag coefficient. That's the only way that viscosity appears in this problem for us. And then finally, there's some, no, I think that's sufficient. I can say more detailed things about what we're ignoring, but you'll see as we go, we're ignoring a lot. Okay, good, here we go. So let me draw a diagram of a boat. So here's, roughly speaking, a sailboat looks like that. This is sitting in the water. And later we're going to treat this thing as a cylindrical object. We're going to actually literally treat it like it's cylindrical because we don't want to deal with the shape, but whatever. And underneath the boat in the water, there is a keel. There's a keel like this that's in the water. That is down below the boat. If we're looking for the top, that's down below the boat inside the water. And outside the boat, above the boat in the air, is a sail. And you can think of me as having drawn the boom of the sail. Here's the mast that goes straight up, and this is like the boom that holds the sail, and the sail is some complex surface attached to that. But we're just going to think about rough, remember I said my sailboat's going to be pieces of plywood. Now, this sailboat is in the water and it's in the air. So in general, there's some velocities we have to deal with. First of all, there's a wind velocity that is coming in. The next thing is the boat itself is moving in some direction. And by the way, contrary to popular opinion, sailboats do not travel in this direction. They almost never travel in that direction. And when you're sailing, you sometimes feel like you're traveling in that direction, but if you're careful and do your observations, you realize you're actually traveling off that direction a little bit. There's a velocity of the boat, and it will generally not be in the direction that you're pointed because, well, of course, it's going to depend on this, right? You see? This one is more locked to the water because it's got a bigger surface in the water. This is a smaller surface in the water. It's less locked to the water. And then, of course, it's also the case that there will be, in general, some velocity of the water. In general, there will be 3 velocities. And remember, I said one of my goals is to be Galilean invariant. So now I'm going to write down a Galilean invariant description of this boat. In order to do that, we need some control. These are control surfaces here. So our fundamental assumption about the boat is that there is a keel with an orientation EK, which is, think of this as a unit vector, which is perpendicular to the keel. And there's a sail with a perpendicular unit vector E sail. So fundamentally, that's supposed to be a K. Sorry, it's so ugly. That's supposed to be E sub K for keel. This is E sub S for sail. You can think of these as unit vectors that point perpendicular to the control surfaces.
You're two-dimensional.
And we're fully two-dimensional. We're only two-dimensional. We're not going to think about the boat. So in some sense, this is a steady low wind model. There's so many crazy things. Actually, these America's Cup boats, it's so crazy. They, of course, put a foil down here, and so they actually come fully out of the water. And so when they're at full speed, the hull isn't even touching the water. They only have keel in the water. And the keels are much longer than this. Keels are like this. And then they come fully out of the water. Actually, I'm not sure if America's Cup does that, but Open Class does that.
They do as well.
I don't really know anything about sailing. That's one of the weird things about this project. Okay, good. Good. So now, what is the ram pressure force on this? And if you think about this object, it is being rammed by 2 fluids. There's air ramming the boat, and there is water ramming the boat. And what's the net force on the boat? So let's just step back, and now it's astrophysics time. So imagine I have a plank. Of course, in astrophysics, you never have pieces of plywood, but whatever. Actually, we do kind of, because we build enclosures for telescopes, and the enclosures for the telescopes are actually, if you've seen the Sloan telescope that Blanton talked about last week, the Sloan telescope looks like this metal box. The telescope looks like a box. That box is actually not touching the telescope anywhere. That box is a windshield that moves as the telescope moves so that the wind never touches the telescope. The wind just hits the box. It's quite similar to in Gravity Probe B or the LISA, how the test masses are inside Shepherd satellites. There's separate Shepherd satellites that take the solar wind and the solar radiation pressure so that the test mass is purely on a gravitational orbit. So similarly with the Sloan telescope, we block it from the environment with a box. So actually we do think about pieces of plywood in the wind in astrophysics, but it's not where you might think. Okay, good. So if I have a piece of plywood in the wind, and there's wind coming at it, and there's this normal vector, E hat, what is the force from this on that? Well, roughly, ram pressure looks like this. The force, and unfortunately I'm talking about forces, I guess forces are allowed. Oh wait, I should look at you. Are forces allowed?
We'll allow forces.
I'm glad because that's all I got. It's a little embarrassing if we don't. There's some coefficient of drag, which might depend on some details about the shape and the surface of this and stuff like that. And then there's rho A, the density of the air or density of the fluid, the area of this plank. And then there are, well, I'm going to write it like this. There's different ways you can now write it. I'm going to write it as E hat dot V. squared times E hat.
This, the wind.
Okay, so let me be very careful. V is the relative velocity of this plank in the wind. So if I'm in the rest frame of this plank, this is the velocity of the wind. This is two factors here. The first factor, you can think of these two factors independently if you like. The first factor is like the rate at which air molecules hit the surface. And the second factor is how much momentum does each air molecule impart to the surface, right? It's like, this is literally first year physics. Actually, when I taught first year physics at Princeton, there was a problem like this on one of the problem sets and I got it wrong. And Bob Austin, if you know Bob Austin, dressed me down publicly on that. So I've never gotten it wrong since. Okay, good. So this is what I call F flat. This is if you have a flat surface that's seeing the wind. Now, this is not strictly, well, this is either strictly correct or not correct at all. It's strictly correct if I allow this drag coefficient to depend weakly on the angle. If I allow this to depend weakly on the angle, then this really does become correct. This thing is dimensionally correct. By the way, dimensional analysis, I should have listed that in my symmetries, dimensional analysis, right? This is a density and an area and a velocity squared. These are unitless unit vectors. Added up, it's newtons. If this thing is dimensionless, this is in newtons, so this is a dimensionally correct expression, so it kind of has to be right. The angle dependence implied by this dot product squared isn't quite right. There's some weird effects which have to do with what kind of wakes come off these edges. And because that depends a little bit on the angle, you actually technically have to put a little bit of angle dependence in there. However, this is a pretty darn good. This is a 0th order ram pressure. This is good enough for all purposes in astrophysics that I know. No one does anything more precisely than that. Okay. People with me? Anybody have a question?
Isn't it like
Am I wrong?
10% accurate because there will be 10% drag for sure?
You mean, yes. Well, this is a drag. You can think of this as a drag.
Drag, lift, whatever.
Right.
You're
There's going to
calculating
be
lift. There is also drag. Right?
Yeah, right, exactly. So right, good. Good. Andre's making a very good point. So if you believe this formula, then this will just float in the wind. Right? There also has to be some component that just goes downwind. We're about to just add it as a separate term. I'm going to add it as a separate term, but Andre's right that you never get this alone. You always have to also get, and this is what in airplanes is called the lift ratio. There's a lift ratio, which is a ratio of this force, the force you want on your wing, to the drag force, the force you don't want. And we're just going to explicitly introduce the drag as a separate term. But you're right. Yeah, good. So that means the net force is not actually going to point exactly in that direction. So I'm now going to introduce the other force just as a second term, and then I'll arrange my board so you can see them. So now imagine I have the same setup. This is very theoretical physics. By the way, this is like freshman physics, exactly in the sense that if you literally think of molecules bouncing off the sail at angle of incidence equals angle of reflection, you get exactly this formula. So it's really a stupid approximation. But it's exactly correct for solar sails. So if this is a solar sail and this is the illumination of the sun, this is exact. Well, if this is mylar, reflected mylar. Anyway, good. Now imagine the same problem. So here's the same problem, except now I have an isotropic object with a fluid velocity coming in. Now I have an isotropic object, like a cylinder in the water. Then there is going to be something which I call F-iso, the isotropic force. And this thing is some different coefficient, I don't know, some other coefficient, rho A. A is now the cross-sectional area that the wind sees of that object, which of course is the same in all directions, no angular dependence. And then you can write this different ways. One way to write it would be it's the magnitude of V times V. That'd be one way to write it. It points in the direction of V, but it has a magnitude which is V squared. So it's this. That's one way to write it. There's different ways to write it. By the way, the right way to write this, oddly, I think is not quite this. Really, the right way to write this is E hat dot V magnitude E hat dot V E hat. This should be translated to this, I believe. Technical detail. It has to do with the fact that you don't know the sign of this normal vector. Ignore that. If you don't know the sign of your normal vector, then you have to use a better expression. Okay, anyway, good. Symmetries. This thing is symmetric to flips, which the other one was. Anyway, okay, good. This, and this again, this is the isotropic force that acts on your cylindrical object, and it is, notice this will have no angular dependence. This eta will depend on the shape and the surface properties of this object. And famously, golf balls are dimpled for some reason that I don't know. But it has something to do with reducing its eta. So like little details of this can matter somehow. But anyway, we are going to treat our sailboat as a sum of these lift terms and these drag terms, and that's it. And that will be the model of a sailboat. Good? Okay, let's do it. So the idea is, here's my diagram. So now what there's gonna be is the total force on the sailboat is going to be a flat force on the sail. Then there's going to be an isotropic force from the air, and then there's going to be a flat force on the keel, and then there's going to be an isotropic force from the water. So you can think of this as like lift on the sail, drag on the sail, lift on the keel, drag on the keel. Good? And now it's just a matter of tuning these eta parameters to get behavior that looks like a sailboat. And I'm not going to talk about that. We chose some numbers. Actually, one of the things we found, which slightly goes against Andre's comment, is that we actually need lift ratios on the order of hundreds for sailboats to sail upwind. I have successfully sailed upwind, and I'm an idiot. And that means that sailboats must have actually very good drag ratio or lift ratios. And I don't understand why. It has something to do with the fact that the sail is curved, nicely curved by the wind. And indeed, our physics of sailing people that hit me on the internets, got mad at me on the internets, were mad at me because they're like, all the details of the shape of the sail matter because it has to have a very high lift ratio. So in fact, these isotherms are actually quite small. We're not going to drop them. We're not going to drop them because if we drop them, we get absurdities. But
yeah, I thought it is 1 for a flat surface, 0.1 for a flat surface.
Yes, that's why you can't just make a sailboat out of pieces of plywood and sail upwind.
Yeah,
So this is very different than for wings. Right?
Wings, they're very related to wings. So it's actually, by the way, just in case, I have to sidebar this because so a plane's wing looks like this, roughly. It looks a little less curved if you're on a jet, a little more curved if you're in a Cessna, whatever. Wings look like this. And there's this old argument about how wings work that think about the air going up and then the air going down and the air going up goes along a longer path and whatever. Those arguments are totally wrong. That is not how wings work. Never think that ever again. It's been completely debunked. There's many papers that debunk it. There's some very clear review papers. It's such a big literature of debunking that there's review papers about the literature debunking that. That's not how they work. The way wings work is that there's incoming momentum and there's outgoing momentum at a different angle. Therefore, the wing feels a lift force. Sails do the same thing. Sails also look like that, but interestingly, sails completely debunk this argument already because notice the path length down this side of the sail is the same length as the path length down that side of the sail. So all of those path length arguments that at least I read about when I was in high school are dead wrong. If you haven't seen that, just FYI, don't ever repeat that. By the way, this also looks very like the cross-section of a propeller. Propellers have this cross-section, sails look like this. Basically all things that are at high Reynolds number and high speed in the air look like this.
Propellers and wings are the same thing. Think about in a bird, they are the same thing.
Exactly.
Part of it is the
Wait, yeah, exactly. Sails, wings, propellers, they're all the same thing. They're redirecting momentum.
And it's a piece of useless information for a pigeon. The lift to drag, I think, is 7.
Right, yeah, actually, birds work hard to fly, and you see them working hard. They don't have huge glide ratios, but in the birds that do have great glide ratios are like albatross that have really long, thin wings. If you want a big glide ratio, you have very big, long, thin wings, and albatrosses can like circumnavigate the world. They have amazing glide ratios. Literally circumnavigate, look it up. Albatrosses can fly across the Atlantic Ocean. It's insane. Insane what birds can do. Okay, good. Good. So now, let's just be a little, I'm not gonna write this all out. If I write this all out, we'll all die. We don't even write it out in the paper. But for instance, if I took this term here would be some,
Sorry, but where is the drag in this formula? You had the lift and drag.
Good. You can think in the engineering literature, these terms would be called lift terms, and these terms would be called drag terms. These terms are drag terms because they just go directly opposite to the velocity, or they're collinear with the velocity. Whereas these are control surfaces that you can turn and then get transverse forces out of. So in the literature, these are called lift and these are called drag. And in fact, in our paper, we talk about lift to drag ratios for sailboats. Although it's a little confusing, the literature about those terms. And in different engineering disciplines, they're used slightly differently. But so for instance, what is this term? This term is rho times some effective area. There's some effective area of the hull. And why do I call it an effective area? Notice there's this coefficient of drag times the area. If I put those together, there's an effective area. This thing is dimensionless, so I can just put it in there and call it an effective area. So there's an effective area of the hull in the water. And then it's V, as I just said, over there. But this V is V water minus V boat, and as is this V here. So those V's are now the velocity differences between the water and the boat. And then this force, that particular, and then I can do the same thing for this. What's F flat keel? F flat keel is this formula here, where this is the orientation of the keel, and this velocity here is the water minus the boat. And then similarly, F flat sail, this E is E for the sail, and this is velocity of the air minus the boat, right? So these two terms depend on V water minus V boat. I might drop.
Introduce V water. Isn't it always along with the wind or something? If you are in the sea, what is your V water?
It's the velocity the sea's moving.
Oh, so you consider sea moving?
The sea, because we're Galilean relativistic. We're trying to be Galilean relativistic. So you can fly over in your hot air balloon, and in your coordinate system, we're still correct.
Oh, you're just using arbitrary coordinates?
I'm just trying to be coordinate free.
reason.
We're trying to be coordinate free. For one of the reasons I want to be coordinate free is just because I claim to my undergrads that you can always write things coordinate free, so I better do it. And second of all, I think it's at least slightly clarifying because, well, we'll see in a second. I'm going to make a definition for what it means to sail well, and the velocities will matter in a second. Like sailing on the river is actually slightly complicated. And then this is V air. This depends on V air minus V boat. And I'm dropping my, well, maybe I'll put them on. Okay, good. Everyone good? Think I'm gonna make it? I'm feeling pretty good. Everyone's with me so far? Okay, so now we have to define sailing. We haven't sailed yet. All we've done is written down forces. Forces aren't sailing. So what is sailing? So sailing is steady sailing, what you might call steady sailing. Steady sailing is F equals 0. This is, by the way, if you're a theoretical physicist, you have to have an equation in your paper that looks like this. This is one thing I've learned from all the brown bags I've been in all of my time. You have to have an equation like that. I mean, at most you can have like h squared is g rho, but it's got to be compact. Anyway, that's steady sailing. We're done. Drop the mic. No, I've got lots more to say. What do I mean by that? I mean that I have to set the velocity of the boat such that this total sum of forces is exactly 0. Now, how do I do that? Well, the first thing to observe is that this is quadratic in velocity, and this is also quadratic in velocity. Some pesky absolute value signs, which might be a little concerning, but this is a quadratic in velocity, and the velocities are velocity differences, so we're quadratic in velocity differences, which means we're quadratic in all the velocity components, so we just solve a quadratic equation. No, I have no idea how to solve this problem. We literally put it into an optimizer and we literally root find it. It's a quadratic equation though, so I have this intuition that there must be a closed form solution, and the solution is so beautiful, as you're going to see in a minute, that it's got to have a closed form solution, but I have no idea what it is. Literally none. Am I stupid? Do quadratic equations have closed form solutions? I'm looking at you, Matt. You're literally on the paper.
It's a degree 6 equation, right?
Well, you can think of it as, a lot of quadratic equations, yeah, if you want. And there's all the cross terms. And then I thought, well, then I can move to like a matrix form, but then it's a little complicated because the absolute value signs. I'm like, ugh. So I gave up. We just root find it with Newton's method. Bam, 2 iterations, machine precision, whatever.
It's two-dimensional, so it's quartic. So
It's
formally the Italians.
Oh yeah, it's a
Yeah,
Ferrari formula.
formally there's a quartic solution.
Yeah, there is the Ferrari formula.
Good, actually, I think that's probably right, but oh my God, that would be painful. Okay, good, that would make our code a lot longer. Okay, good. Oh yeah, so now, if you ask, okay, so now you can do the following thing. Imagine you are a complete idiot, which is an approximation to how I used to sail. I was a very successful competitive sailor when I was 14, but that just shows that everyone else was even more useless with ropes and pieces of canvas than I was. What we're going to do is we're going to plot, so here's velocity in one direction, which we could call x, or I could call the wind direction, because we're going to make the wind point that way in a second. And here's velocity in the y. So I'm just plotting the components, the x and y components of the velocity. And here's 0, 0. So this would be a boat that's not moving. Okay? And we're going to be we're going to go into the water. So now we'll go into the water frame. We're Galilean relativistic, so I have to say all the velocities, which is a bit annoying. Here's going to be the wind velocity. So this arrow here, I'm going to label the end of the arrow with v wind. So this is the wind velocity. Okay, and now I'm going to put this in the v water, just for Andre's sake. I'm going to set this in the v water of 0 frame. So we're going to go into the rest frame of the water, just so I don't have to think about the water as well. And now, if I did the stupidest thing I could possibly do, which means I just set the angles of the keel or the boat, I turn the boat to random directions, and I put the sail at random directions, and I just ask, what happens? Because if you just fix everything, these are rigid pieces of plywood, although not really, because then the drag ratios wouldn't work, but whatever. These are just rigid things. I can just set them to random values and just ask, how do I sail? And of course, sometimes you sail backwards, sometimes you sail sideways, whatever. Okay, now one comment is, you cannot sail at 0 velocity. 0 velocity is not an option. And the reason it's not an option is you have some hull above the air, in the air, and so you always have some ram pressure from the wind. So you cannot sail at 0 velocity. That's not an option. You will not be allowed to do that. You have to move relative to the water if the wind has velocity with respect to the water. And of course, the difference in the velocity between the wind and the water is the free energy that you're working off of. When it's there, you can't avoid, but you can't help but use it. You have to use it. So the worst you can do is called luffing. You take your sails and you point them directly downwind, so the wind is just blowing over the sail like this. That's luffing, and when you're luffing, you actually move downwind very slowly. And you also can't go, you're about to complain about something I said earlier, you actually can't go downwind quite as fast as the wind, directly downwind. And the reason is, imagine you just put up your sail perpendicular to the wind and try to go downwind with the wind. Well, you still have some of your boat in the water. There's the hull in the water. There's a drag force in the water. And so the water will not let you go downwind as fast as the wind. So if this problem were one-dimensional, we'd be done. And in the one-dimensional sailing case, you cannot sail upwind, you cannot sail down, you cannot sail at zero velocity, and you cannot sail downwind faster than the wind. The one-dimensional world sucks. And we know that, right? Because if the world was two-dimensional, we'd be in flat land, you wouldn't be able to, like, the part of your body that's attached to the top of your jaw wouldn't be able to be the same as the part of the body on the bottom of your jaw, and so similar things. Sailing's really boring in flat land, so that's out. Okay, so now, if we now set to arbitrary angles, it turns out there's a figure that looks like this. Actually, I've drawn it badly. These really look like circles. These are basically circles. And these are all the different velocity vectors that the boat can have with respect to the water. You with me? So what am I doing? I'm solving this equation. That adds up to 0. I'm solving this equation. All the solutions to that equation live inside this hourglass shape. And notice that there are vectors that cross this way. You can sail upwind. And there are vectors that cross the wind velocity. You can sail downwind faster than the wind in general. In specific cases, now I'm going to show you some specific cases in which that isn't true. But anyway, this is the fundamental result of the paper. By the way, this shape is drawn in all the books. Every book we looked at about sailing has this figure in it. So it was kind of amusing when we recovered that figure. And some of the books claim to actually have that figure based on data, although none of them show us the data. So I'm suspicious. Now, there are some books that claim that you cannot sail downwind faster than the wind with a sailboat. And I'm just going to talk about why I think they claim that, even though it's obviously wrong. We literally just write our stuff down and we solve the equations and we get it. By the way, there's so many things to say here. Some people don't take this as an argument that you can sail downwind faster than the wind because you have to tack the boat. You see, you can go downwind this way and then you have to tack the boat and go downwind that way and that way and that way. And so you'd have to tack all the time to go downwind faster than the wind. But since you can have a set of boats doing that, pulling a barge or whatever, then in fact you can move the barge downwind faster than the wind. So we believe that this solves that problem, but the problem's been solved by others in other ways.
But this possibility of faster than the wind is, what do you call it, contingent on this lift to drag ratio. So for some
I'm just about to talk about that.
Oh, okay.
No, I'm about to talk about that. The drag ratios or the lift ratios matter a lot here. And if your lift ratios are bad, you cannot go downwind faster than the wind. And if your lift ratios are bad, you can't even go upwind. So one of the things that's interesting is that you can easily sail upwind. Idiots can sail upwind. That means the drag ratios are pretty good. That, of course, doesn't by itself mean that you can sail downwind faster than the wind. I'll tell you why in just a second. Anyway, questions about this? Yeah.
Is there a nice understanding of how much faster than the wind downwind or how much upwind you can travel?
Good. I'm going to answer that in just a second. I mean, I'm not going to be very specific, but I will tell you what comes into that question. Okay, good. Good. So one thing we did is we did exactly play with these drag ratios or these lift ratios and also the relative size of the sail and the keel. So let's go to a boat. That diagram, notice I've drawn this diagram very symmetric. You see the amount I'm pinched in here is the same as the amount I'm pinched in here, and the amount I go over this line is about the same as the amount I go over this line. This diagram that I've drawn here is for the effective area of the sail over the effective area of the wind, of the keel, to be 700. At 700, this looks really symmetric. Would anybody like to tell me why? What important fundamental quantity is 700? 700 is an extremely important dimensionless quantity in your life.
Ratio of densities.
Ratio of densities. That water density to the air density. That's extremely important to know. That's why an asteroid can make it, some big asteroid can make it through the atmosphere, but stops in the top layer of the ocean. Ocean's way better than the atmosphere for stopping rocks flying in. 700, that's a big number. So at this number, at this density ratio, this effective area ratio makes this a very symmetric diagram. And it turns out this ratio is incredibly good for sailing crosswind. So we find that it's optimum if you're trying to sail across the wind. This is the ratio you want. And actually, if you watch in America's Cup and other races, they re-rig. They do legs of these races that are in different directions with respect to the wind, and they re-rig when they change their legs of the race. They re-rig. What do they re-rig for? They re-rig to optimize this ratio for what they're
Are
doing.
you sure Lord Kelvin didn't do it 200 years ago?
This?
Yeah.
I'm sure he did. He just didn't
Right.
publish it.
Oh, he didn't? Oh, you
To our knowledge, we've been looking. There's actually the closest to this model, if you're talking about this model, the closest to this model that we find in the literature is there's a very good book that is one of the ones I really love that's filled with engineering details. And they have a little section in like chapter 15 in which they say, by the way, you could make a pure model that was just like momentum driven wind, like a momentum transfer
You have
model.
looked and you did not find it?
And they said you could make that model, but it would never make useful predictions for a sailboat. And they didn't write down the equations. They just said you could think about a model in which you think about the momentum impacting the boat. No, we can't find it. I mean, maybe it's out there. It probably is out there. I mean, people have been writing about these things since the 1700s.
Maybe what is light hail?
Why
No,
did they think
the location
Say
professor
Why do they
before
think it's light?
talking.
I don't know. They
Great
think that the
expert
details
of,
matter. I think they're just wrong.
hydrodynamics.
It's the Twitter people.
Similar to the Twitter reel. But my claim is that if you're a cosmologist, if you're an astrophysicist, actually cosmologists are now doing precise things, so I gotta let them off. But if you're an astrophysicist, you don't care about anything to better than a factor of 2-ish. This is certainly good to a factor of 2. Okay. So now you can ask, what happens if you change the various ratios? So so for instance, imagine I just change from 700 in this ratio to something more like, 50 or whatever. Then what happens is what happens? You've just increased your keel relative to your sail. Of course, we compute it and we compute another curve. But if you just think about it, you're more locked to the water now than you are to the air. And that means that you can move more with respect to the air than you can to the water. And this whole figure moves this way. So if you increase the size of the keel, the whole hourglass shifts that way. And it's kind of obvious because it's always differences of velocities and times air effective areas. Anyway, there's some reason that should be obvious, but I can't quite explain it. And notice now you can sail upwind much more easily. There's many more settings of your. Oh, sorry, this is wrong. I got this wrong. This comes down and goes like. It does some crazy thing here, which I don't fully understand. But anyway, it does some crazy loop there. But this part of it looks identical. It actually shifts. This is a perfect shift. And then something pinches here because you can't. Good, nice catch. I'm trying to remember the figures in our paper. But the important thing is it's way easier to sail upwind if you have a big keel, which is our explanation of this choice to make commercial sailboats very easy to sail. It would be very frustrating if you buy a commercial sailboat and then you can't get home. You sail out and then you can't get home. They have to come rescue you. So this is like important for drunk sailors. And you're usually coming home drunk, so it's really important. Actually, that's illegal, I think, in New York State. Anyway, by the way, this is one of the reasons I believe that some sailors believe you cannot sail downwind faster than the wind. Because commercial boats are biased to upwind sailing, and when you bias enough to upwind sailing, you lose the downwind faster than the wind sailing. Good.
What about the other case of a much bigger sail?
Good, much bigger sail. So now if you go to bigger sail, the opposite thing happens, and now this becomes, bigger sail looks like this. But bigger sail, so that is a really beautiful diagram. I'm sorry, I apologize. Good, bigger sail shifts it all this way. So you might think, okay, cool, now I can sail downwind much faster than the wind. The problem is we believe that if you go to very big sails, you can't do it without killing your drag ratios for all the reasons. So we think that if you go to the bigger sail, you'd also increase the isotropic air force, the drag force, and that might kill all this advantage. There's a best size for your sail. And I don't think it's going to be much bigger than this. And if you look at the way they sail it competitively, it looks like they do saturate around here. You don't see things that look much bigger than that. Yeah.
So small boats, you can have the keel go to 0, right? Because you can play with it.
Yes, yeah, with the centerboard,
Then
you
this
can pull it
ratio
up.
goes to infinity. Then what? But you typically
Ah.
don't sail that fast downwind.
If the ratio goes to, yeah, if you pull the keel out entirely, the boat doesn't really sail anymore. You kind of just go downwind. And how well you go downwind depends on the orientation of your sail, which is hard to maintain because your boat blows around. But yeah, it's kind of interesting to think about the limit that you have no keel. Because he's absolutely right. If you are in little boats like Sunfish or whatever there, you literally have a centerboard you can pull up and pull down. And it makes me wonder if we could have sailed better competitively when I was a kid by actually pulling up the board sometimes.
But they do, they pull them up.
They do. When you're going down, straight downwind, if there's a leg that's straight downwind, people pull the boards. They do, yeah. And we did that, but there's other things where you might want the board in halfway. That's what we were
So
realizing.
it's actually allowed in
Yeah.
sport sailing?
Yes, well, it depends on the class, but yeah, I mean, when I sailed when I was a kid, we were in these shitty little boats that had little centerboards. And it was just so that we could pull the boats up on the beach. They weren't centerboards for some technical reason. It was just like, because you have to store the boats. So we could pull up the centerboard. We would do it to go downwind, but, and then water comes in the boat too, through the hole.
But like competitive 420s, that people play with it depending on the leg.
Yeah, the other thing that people talk about in the sailing literature, most boats don't have a movable keel like this, but you actually want to do something with the tiller when you're sailing hard. So when you're sailing these lines, you actually want to have some pressure on the tiller for this reason, for some reasons that are also about adjusting the details of this underwater force. I feel like I had some other.
So
Oh
this-
yeah, I have one more.
This boat doesn't have a rudder.
Our boat has no rudder, right? Our boat is just 2 control surfaces. Okay, it kind of sucks. But you know, yes, we don't tell you how you change directions, but you have to have some way to do
But
that.
that doesn't affect.
For
if you
us,
add
it
the-
doesn't affect anything because our model's so brutal. But in reality, right, now I'm going off script. In reality, sorry, trying to do it out of line. There's a curved sail here, and in reality, you actually curve this by putting a little bit of rudder like that, so you have a curved. You actually have underwater. You have a very slight bit of curve, and here you have curve, and then in the America's Cup boats, which have this much smaller thing, they have a little fin at the back they can turn or put pressure on when they sail.
So how do you position your sail to go upwind faster than the wind?
Good. Oh, upwind faster than the wind we can't do. All you can do is go upwind.
No, sorry, I meant downwind faster than
Downwind
the
faster
wind.
than the wind.
How should I put my sail?
Okay, good. Good. I have one other thing to say, but I'm just going to postpone and say that, and if I run out of time, it's fine. So let me say one thing. So I used to have problems about sailing on I teach Physics 1 a lot. Physics 1 is my favorite class. It is the best class to teach in the whole physics major sequence. It's so great. And I have some usual problems. And one of my problems was a sailing problem that was about the orientation of the sail and the keel. And all of the students found it unbearably difficult and never understood it. And it was always a mess. And then when we started realizing, writing this paper, I was like, okay, maybe that homework problem was a little too hard for the first year undergrads in their first semester. But my picture is this, that comes from that. So my picture is sort of this. So you can switch into a frame. So in this, remember we're Galilean invariant, so I can choose my reference frame. So I can choose a reference frame such that the momentum flux from the water looks like this, and the momentum flux from the air looks like this. For a what do I mean by momentum flux? I mean rho times A times V.
You mean force?
I sort of mean force. I don't quite mean force because I'm now about to put surfaces in here to get the force. So I really just mean rho AV. Now, if I want to move that way, and I've got this, what do? I put a wedge in between the two things, and that wedge gets squeezed by the momentum flux and it shoots that way. That's how a sailboat works. A sailboat is just a wedge being pushed on, and this is also how you navigate with solar sails, although in one case it's the radiation from the sun and this is gravity from the sun, but you can then you're always kind of, in these sailing situations, you kind of have a wedge like that. So now,
So sorry, this is really rho V you're saying, right?
this is rho AV, rho A effective V, because it's the amount of momentum you're intercepting.
But A is given by your wedge, no?
Yeah, I mean,
Oh, you mean something intuitive?
I mean, yeah, I'm
precise,
being
okay.
intuitive. Yeah, I think there's a right thing I could write, but something like that. Now, so how do you sail in that direction? So first of all, in the paper, we have, by the way, very, very helpful diagrams like this that show you velocities, angles of the sail and keel, and which direction you sail and how fast. So useful diagrams like that. But now you're asking me a very specific question. Okay, so first of all, you more or less point the boat in the direction you want to go, but it's not quite that. And then you set the sail very, very tight. It's like this.
And the wind is from this side.
I have the wind going like this. It is not this. So when I was sailing competitively, poorly, we would sail downwind like this. That's how we sailed downwind. Our boats sucked. If you have an America's Cup boat, you sail at an angle with a very tight sail. And you sail faster like this than this towards your destination.
Jane, is that right? Because the top diagram, because when you're going downwind faster than the wind, there's a headwind, apparent headwind going the other way, right?
Oh shit, you might be
I
right.
think the sail should be on the other side of the keel.
You might be right. Yes, because good, very, very good point. Let me just say that. Oh, I wanted to say one physiological thing about sailing. I want to distract you away from my mistake by saying a physiological thing about sailing, which is when you're sailing and you're sailing downwind like this, you feel like, I can tell you from direct experience, you feel like you're making no progress at all. You're in the water, you're like, God damn it, will we ever get there? And then when you're sailing upwind, into the wind, you feel like you're just hauling ass. You're leaning off the back of the thing and there's wind blowing in your face. Why? Because when you're sailing upwind, you feel the wind in your face. And when you're sailing downwind, you feel basically nothing. And so similarly here, if you go faster down the wind, then actually relative to the boat, the wind is coming at you. Okay, so now I have to get it right. I'm not sure I'm going to get it right.
Andre, this doesn't answer your question about the angle.
Yeah, no, it's this way.
No, because
You're right, it's
to
very
solve
tight.
aquatic equation and to understand why you can go faster than the wind,
Are
at least
different
to
things.
me are different things.
They are, I agree
Right,
with
but
Andre.
there's
I'm
a
so
way
with
to
Andre.
understand it that won't tell you the angle, but makes it clear that
Good.
it's possible.
It's gotta be this.
And what is the wind?
The wind, well, the wind is going this way relative to the water, but relative to the boat, the wind is coming in very lightly like that. Relative to the boat, actually, it's coming in like this. Because the boat's moving up a little bit. So the wind is coming in slightly upwards. It comes off this and then yeah, something like that. I don't know exactly.
So Andre, if you can sail upwind at all, that means let's say you're in the rest frame of the water and there's a headwind and you're sailing into the headwind. So if you want to know if you can sail downwind faster than the wind, you can transform to the frame where the water is moving and the air is at rest. And so now there's a current coming towards your
Now
boat.
there's a current pushing you that way.
So you claim you do have some intuitive understanding of why
Yeah.
it is possible.
Yeah, if you believe you can sail upwind, then you also believe you can sail downwind faster than wind because they're actually the same. They can just reverse the air and the water.
Hence, my hourglass was symmetric. When you set this ratio correctly, the hourglass is symmetric, so it's actually the same to sail upwind. Yeah.
When you say faster than wind, does that mean the magnitude of the velocity is faster or the velocity in the direction?
Good. So this question, sorry, I'm out of time. But this question is whether you actually make downwind progress faster than the wind. So it's about the vector component. Sailing faster than the wind is easy. Everyone can sail faster than the wind. You can sail this way faster than the wind easily. But sailing downwind faster than the wind is the hard part. Sailing faster than the wind is not controversial, actually. All reasonable sailboats can sail faster than the wind, transverse. I think I'm out of time.
More questions?
Yeah.
So I think in real life, like the water velocity will be more like correlated with the wind velocity. So
Say one more time.
so in real life, your
Yeah.
water velocity will more or less be correlated, at least at the surface of the water, it will be correlated with your wind velocity, right? And in that case, could you sail faster than wind?
You mean
So
like waves on the surface
Yeah,
blown
yeah.
by the wind.
Ah.
So there will be a surface flow of
Good.
water. Right?
Good. You're asking about this velocity shear type question.
Yeah.
So there's a bunch of velocity shear type questions which are non-trivial. One is that the surface of the water is moving closer to the wind speed. That hurts you actually, because fundamentally the sailboat works on the difference. Notice this vector that I said was v wind is really v wind minus v water. That's what drives the sailboat. If I make v wind minus v water bigger, this whole hourglass gets bigger. And if I make it smaller, it gets smaller. So the fact that the two wind speeds get correlated near the surface actually hurts you. And that's one of the reasons I think that sails are tall. You could make sails this way, but people make sails this way. And I think it's partly because you want to get up there into the stronger, into the bigger. It's also, but the weird thing is commercial sailboats like this one are actually much more tied to the water than the air. They're really locked into the water. And so it's a lot of it is about the water speed, I think. Yeah.
Do you have any intuition? So, I mean, you're saying you could build boats that do this, but are there boats that do this?
Downwind faster than the wind, this downwind faster than the wind here is controversial. It's quite hard to measure, but I do think that the professional sailors claim that you should sail. So there, I did find in the reading I did, claim that you should go downwind like this, not like this.
Yeah, there's America's Cup boats that can do this.
They
and
can do
there's
this.
ice boats that can do it.
Ice boats are,
3 or 4.
yeah, ice boats are ridiculous. They're in a weird regime. Ice boats are in a really weird regime where you can do a lot of weird things because you're truly locked in.
You very little drag in the water. Well, there's
Yeah,
hardly
you
any.
essentially have infinite drag ratio or lift ratio. So, right, there are claims that you should sail like this, but I think very few people can do it. I think it's extremely technical.
In the water, it's really hard.
But it's certainly said in those books. Actually, one of the best books in physics of sailing is actually just about sails. They're only about sails, because a lot of the physics comes into the sails. The sails are the places where the sailor has a lot of choice. And a lot of the work is done with the sails. So they talk about how you rig your boat to do this. Because you make different choices with rigging.
But from what you're telling, the keel is as important as the sail, so
It
why
is.
don't they make
I know. I know. As we learned, they do that for the professional boats. It is very interesting whether there are things you could do here. Now, of course, there's all sorts of, these are fiberglass, single unit fiberglass holes, so they don't want to mess with it. They don't want to put holes through the, like you have to put a mechanical linkage with a grommet and stuff through here. So I think there's a lot of reasons from a boat maintenance point of view that you just want a rigid keel.
And stability.
Say again?
And stability. I mean, you don't want to capsize.
Yes, you can also
it,
create new instabilities. Yeah, this boat is super stable. It will, even if you sail like an idiot, you'll never capsize it, whereas this thing capsizes easily. In fact, they capsize all the time. So I think there's a lot of reasons they don't mess with the keel. But frankly, there might be simple things. And the one thing that I did read about in the books was this thing about how you manage your tiller. They said, if you're sailing with a straight tiller, you're probably making a mistake. They say you should keep some pressure on the tiller. There should be a pressure on the tiller, which relates to how you're rigging. It also depends, by the way, it depends in a really weird way on where the mast is, right? Because there's a center of momentum.
That's because of the torque, right?
You want certain kinds of torques because you want to be doing this to make the curvature you want here. But that means it's going to apply a torque, which you want compensated by your sail.
But that's the second equation, right? Because you only roll the equation for the force, but torque also has to be
Good.
zero for.
Very good. Torque has to be zero as well. And it's actually very nice to add the torque, actually just to add the, And the other thing that I think we could add probably is the 3 dimensions, like the fact that the boat, like they work very hard in the America's Cup boats to keep them from leaning. They're literally way out on this armature. They climb out on this armature to try to keep the boat as level as possible. I'd like to understand that. I don't fully understand that.
It's mainly to stop from capsizing.
And maybe it's mainly to stop it from capsizing.
You have to do that on a regular.
You do, but it is interesting how hard they work at it. We used to let it go up to, good 40 degrees when we sailed, but I think that's not a good idea. I think you want to keep it vertical. Yeah.
How much more on the left can you take this rod? This keel?
You mean like, can you go upwind really fast?
Right.
Don't know. I think you certainly cannot, but as far as I can tell, you can't go upwind faster than the wind. So I don't know. I don't even know how to think about it. But there might be a fundamental limit. I think there must be a fundamental limit. Although the weird thing is, if you let the lift ratios go to 0 or to infinity, if you let the lift ratios go to infinity, there are absurdities here.
I don't think there's any limit like that.
Maybe it just keeps on going. That would be weird, but it might be.
Oh, nice.
I mean, he's a real believer. Claiborne's a real believer that there really is always free energy, and you're only limited in taking free energy by your drag forces. So if you get your drag forces down to 0, you can take arbitrary amounts of free energy out of the system.
So there are wind carts, land-based, with wheels and.
Yeah, with wheels on the
that
salt
go
flats.
Yeah, they go upwind faster than the wind.
Faster even than the wind.
Yeah.
Wow.
Yeah.
Okay, so then there's no limit.
Speed of light.
Speed of light. I think speed of sound gets you first.
I think that this discussion could contain more about.
Yeah, sorry,
Right
we should go
discussion
in.
for the
We
setting.
should, literally,
Yeah,
yes.
let's thank David again. Yeah, there's coffee, cookies, and
Probably, didn't Einstein have this model with a cylindrical sail that rotated?
Yes, and there are some really weird non-trivial sails around.
Even him has, you have a cylindrical wheel that rotates and the